Two equations draw two constraints. Sometimes the lines cross once, sometimes they collapse onto the same line, or never meet at all. Before we solve for x and y, can the matrix itself tell us whether one answer will survive? It can. A single number acts like a warning light for a square system. That number is the determinant. In the previous lesson, rank counted independent information. Now the determinant will tell us immediately whether a square matrix has kept all of it. Start with a coefficient matrix for 2x plus 3y equals 3 and x minus 2y equals 5. To ask for its determinant, replace the square brackets with determinant bars. For any 2 by 2 matrix with entries A, B, C, and D, multiply down the main diagonal to get AD. Multiply down the other diagonal to get BC. Then subtract AD minus BC. Here that is 2 times -2, minus 3 times 1. The result is -7, non-zero. That does not solve the system yet, but it guarantees that exactly one solution exists. Why is this one number so useful? Because the two products compare the matrix's two competing diagonal pairings. If they cancel exactly, the determinant is 0, and the coefficient rows do not supply two independent constraints. If they do not cancel, the determinant is non-zero, and the rows are independent. For a square matrix, that is the key diagnostic. Non-zero means full rank. 0 means rank has fallen below the size of the matrix. The determinant is therefore not merely an arithmetic answer. It is a compact test for whether information has collapsed. Before moving to 3 by 3, collect the rules that make larger determinants manageable. Swap two rows and the determinant changes sign. Multiply one row by a number k, and the determinant is multiplied by k. Add a multiple of one row to another row, and the determinant does not change. If two rows are equal or proportional, the determinant is 0. A row of zeros also forces 0. And for a triangular matrix, every entry below or above the main diagonal is 0. So the determinant is simply the product of the diagonal entries. These are not decorative facts. They let us simplify a determinant while tracking exactly what happens to its value. A 3 by 3 determinant contains 9 entries, but its calculation can be reduced to familiar 2 by 2 pieces. Choose one entry. Cross out its row and its column. The 4 entries left behind form that entry's minor. The cofactor adds a sign to the minor. The signs alternate like a checkerboard, plus minus plus across the first row, then minus plus minus, then plus minus plus. So the cofactor in row I, column j, is -1 raised to I plus j times the corresponding minor. The checkerboard is the bookkeeping that preserves the determinant sign. Now, calculate this determinant by expanding down its third column. Multiply each selected entry by its cofactor, then add. The top entry is 2. Its sign is plus, and its minor has determinant 7 times 1 minus 3 times 2, which is 1. The middle entry is 4. Its checkerboard sign is minus, and its minor is 1 times 1 minus -5 times 2, which is 11. The bottom entry is 5. Its sign is plus, and its minor is 1 times 3 minus -5 times 7, which is 38. Therefore, the determinant is 2 times 1 minus 4 times 11 plus 5 times 38, 148. This procedure is Laplace expansion, also called cofactor expansion. It exists because an n by n determinant can be expressed as entries from any one row or column, weighted by determinants one size smaller. Those smaller determinants can be expanded again, until only 2 by 2 calculations remain. The value is the same no matter which row or column we choose. So choose strategically. A row or column containing zeros eliminates terms before any arithmetic begins. Laplace expansion is not a new disconnected trick. It is a pathway from a large determinant back to the 2 by 2 rule we already trust. Return to our two equations. The determinant of the coefficient matrix is D equals -7. Cramer's rule solves for one unknown at a time by replacing one coefficient column with the answer column. To find x, replace the x column with 3 and 5, leaving the y column unchanged. The new determinant, d sub x, is 3 times negative 2 minus 3 times 5, which is negative 21. Then x equals d sub x divided by d, so x equals 3. To find y, restore the matrix and replace the y column instead. D sub y is 2 times 5 minus 3 times 1, which is 7. Thus y equals d sub y divided by d, which is negative 1. In general, for n equations in n unknowns, d is the determinant of the coefficient matrix. To find the kth unknown, replace column k by the right-hand side column, call the new determinant d sub k, and divide d sub k by d. The method is valid only when d is non-zero. Its strength is conceptual and selective. It gives a direct formula, and it can isolate one requested unknown without completing an entire row reduction table. For large numerical systems, it is usually not the fastest computation, but in symbolic work, theoretical arguments, and small systems, it makes the dependence on the coefficients remarkably explicit. Now, let the second coefficient row become exactly twice the first. The determinant is 0, and the coefficient matrix has rank 1, not 2. Cramer's rule stops because division by d would mean division by 0. But 0 determinant does not automatically mean no solution. The right-hand side decides what kind of failure remains. If the equations are 2x plus 3y equals 3 and 4x plus 6y equals 6, the second equation repeats the first. The lines coincide, and infinitely many solutions remain. If the second right-hand side is 7 instead, the coefficients still describe the same left-hand side, but the demanded result conflicts. The lines are parallel and distinct. There is no solution. Rank states the distinction precisely. For a square n by n coefficient matrix A, determinant of A non-zero is equivalent to rank A equals n. The system then has one unique solution for every right-hand side. If determinant of A is 0, rank A is less than n, so a unique solution is impossible. To distinguish infinitely many solutions from none, compare the rank of A with the rank of the augmented matrix. Equal ranks below n mean the system is consistent with free choices, hence infinitely many solutions. If the augmented rank is larger, the right-hand side adds a contradiction, so there is no solution. The determinant detects lost independence. The augmented matrix tells us what that loss does to the equations. The story now closes where it began, with two constraints and a question about whether one answer survives. Determinant bars turn a square matrix into a diagnostic number. The 2x2 rule builds the foundation. Minors and cofactors extend that rule through Laplace expansion. Cramer's rule uses related determinants to expose individual unknowns. And rank explains the decisive split. Non-zero determinant, full rank, one solution. Zero determinant, reduced rank, and then either infinitely many or none. One compact number cannot solve every problem, but it tells us, before we begin, what kind of solution story is possible.